we have, on the one hand, time as we tend to think of it in physics, and on the other hand, time as it sort of presented to us in our immediate experience. As many people have remarked, these two seem to have pretty different features and different properties. And the question then is, to what extent do the features of our experience of time, things like the present having a special status different from the past to the future, the passage of time, the notion of sort of objective becoming, to what extent can all of those be explained by current physics properly understood? And of course, there are many philosophers and some physicists, Jim Hartle, for instance, has written on this, who have argued that if you understand the position of a certain kind of observer in space and time, doing certain kinds of things, that you can make sense of how we would come to represent time to ourselves in the way that we do. But then there are other people who would argue that that kind of story is essentially unsatisfactory, and really that there's new physics needed to make sense of what appears to be an explanatory gap. And just to give an example of the kind of thing that some people have argued is an example of new physics that could do this, would be the kind of dynamics you get in causal set theory, where you have a kind of dynamical sprinkling of new events and a kind of leading edge, if you like, of becoming. Now, I'm not sure that this is a particularly compelling physical story, but it's an example of the sort of thing that could provide some further explanatory resources to make sense of these, this gap between time as we think of it in sort of ordinary life and time as we seem to be able to represent it in physics. And I think that the real question is, to what extent is that further new physics necessary? To what extent is there really an explanatory gap, and to what extent is it the case that if we just reflect on what we can get from physics, we should realize that we ought to be satisfied?
Bernard. I take the view that consciousness is fundamental and it's important to somehow accommodate it within physics. In particular, the passage of time is a key reflection of that. I take the view that standard relativity theory and standard quantum theory alone cannot provide that description, so you need some deeper paradigm of physics, maybe quantum gravity or maybe something not quite as deep as that. Now, my own particular interest is that I feel there is one aspect of the passage of time which is really crucial, which is actually hardly ever mentioned by physicists, it's mentioned by philosophers and psychologists, and that's the concept of the specious present. This is an idea that goes back to William James and Henry Bergson. But the idea of the specious present is that our consciousness only comes in discrete minimum amounts, which for a human being is something like 1/10 of a second. And so when we experience time, it's only a very narrow range of scales. If you can imagine a little light going around, you see it going around, or just watch my finger. If my finger goes around more than 10 times a second, you don't see it going around. It's just one continuous circle. And if my finger goes around very, very slowly, less than about once every hour, you won't see it moving either. So conscious experience only exists over a very narrow range of timescales. And then the question is, well, that specious present can change. We know that time can go faster or slower in different circumstances. And furthermore, why do we assume that the only experience of consciousness in the universe is on that very narrow range of timescales, seconds to hours, which humans experience? Why can that not be a form of consciousness, for example, a specious present on the timescale of a microsecond? Why can't computers have consciousness with a specious present of a nanosecond or a microsecond? Why can't there be forms of systems which have a specious present which is millions of years? So I think the crucial thing about physics is we've got to get specious present into physics. I have my own theory as to how you can relate the specious present to physics, but that's a bit crazy, and I'll talk about that in the discussion at this time.
So my name's Jayne, and I'm actually a quantum physicist. So I firmly belong to the camp of the Church of the Higher Hilbert Space, which is to say I believe that the universe evolves unitarily in a pure state. And when I was asked this question last night, my first impression of it was to say that, well, if there's an arrow of time, or a thermodynamic arrow of time, in which we seem to perceive the universe as evolving in a non-symmetric way, then I would say it arose more or less from our ability to, or our inability to track all the information, such that we were forced to trace out some of the events and lost track of everything that was happening, and therefore confounded that in some way for the production of entropy. So I was told this morning this is a rather prosaic view for such a distinguished meeting. And I guess it is, because it comes back to an argument between Boltzmann and Loschmitz a long time ago, where when Boltzmann proposed his theorems about entropy and entropy always increasing, what he did was he derived a formula which suggested entropy in an ideal gas always increased. But Loschmitz turned around and said, well, you know, if I have a complete description of the system at some future stage in time, then in theory I can reverse the velocities of every single particle in that cloud of gas, and therefore I can actually make it trace out the inverse trajectory. And surely if entropy increased in the forward direction, then entropy will ultimately decrease in the opposite direction. And apparently Boltzmann's reply to that was, well, go ahead and reverse all of them. So I think this captures the idea for me that what happens when we have a finite memory capacity, a finite ability to track information, and ultimately, as we track it and have some kind of representation of the environment in our mind, what happens is we're forced ultimately to make some compromises in which we don't record everything properly, because we only have a finite capacity to do so. So what happens is there's a number of calculations upon this topic. People calculating and speculating that the size of the universe which we can keep track of reliably is as small as 10 microns. If you calculate or keep track of all the potential bit flips, the bit flip occurs on the scale of a Planck length up until the current age of the universe. And if you use all of the atoms in the universe to actually keep track of that information, 10 microns is about your limit, about what you can store and at this stage actually understand and comprehend and potentially reverse. So in the frameworks that we like to understand, we can say that as an agent to actually extract work from this environment and to operate within this environment at optimal thermal efficiency actually has to keep a representation of the environment, a complete representation of the current state of the environment. And if they're actually forced to have a limited memory capacity such that they can't fulfill this ideal paradigm, then ultimately what will happen to them is they'll see their environment getting more disordered and they won't actually be able to extract as much work from it. So this would lead to a perception of entropy increasing and a perception that things are heating up in some way.
Thanks.
Hi, I'm Carlo Rovelli. I fully agree with Jim. I fully disagree with Bernard. And I fully agree with Jayne, with some caveat that I might raise in a debate later. I do think that time is real. I think that we get confused about time because we confuse levels. I've written a book on time, so this is my advertisement. This is my book on time. Buy my book on time, everything you want to know about time. And I try to synthesize the book in 30 seconds. The message of the book is that when we talk about time, we're talking about a lot of different things, a constellation of things, some of which refer to our experience, some of which refer to the movement of clocks, some of which refers to our fundamental picture of reality in physics, and so on. And it's not the same thing, because the experience that we have of time depend on the way our brain works, depend on our emotions, depend on a lot of stuff, which has nothing to do directly with elementary physics. When we take ourselves out and we go to what we measure in a laboratory, we lose some of the feature of experiential time, just because we are not measuring human beings, we are human things. When we discard thermodynamics, we go to mechanics, we lose other pieces of time. When we go to general relativistic description of the universe, we lose more. When you go presumably to quantum gravity, we lose even more. I think we make a mistake if we take our full experience of time with memory, anticipation, hopes, and so on, species present. James was a psychologist, and try to force elementary physics to have aspects of our experience which are complicated things of our experience. There are things which are real, time is real, cats are real, but there are no cats in elementary physics.
I think that there are different ways, there are different sorts of reactions that you might have to this analogy with cats. I agree that cats are real. I agree that there are no cats in fundamental physics. I also think that the quantum measurement problem is a deep one, and one that we don't really have a fully satisfactory solution to. And so somehow it can be the case that we have all sorts of partial stories about how we get to cat-like phenomena from our understanding of microphysics without perhaps having a completely satisfactory picture. And I think some people, I tend to feel this way myself, would think that there is something missing. I mean, the measurement problem is a problem of physics and something that we don't really know how to answer. And the question is, to what extent should we take that conclusion over to issues related to time? So to what extent is it the case that we could, in principle, just given current physics, have a perfectly satisfactory story about how, even though the species present, say, or the passage of time isn't part of fundamental physics, nonetheless we could explain, how it comes about in certain domains.
Yes, I'd like to focus on what Carlo mentioned about the fact that William Jaynes was a psychologist. That's true. And of course, the whole point about this problem is that it does involve an interaction between psychology, philosophy, and physics. And I mentioned the species present because it's an example of something which the psychologists talk about and the philosophers talk about a little bit, but the physicists don't talk about at all. And I think that's a mistake, because I think you'll only solve the problem of consciousness and the flow of time from a physicist perspective if you have some concept of the species present. The point is that the flow of time, even the experience of self-identity, only makes sense with respect to a certain level of species present. And if you're on a shorter or a longer species present time scale, you do not experience the flow of time at that level. So that's why I think it's absolutely fundamental. And also you're comparing physical time to mental time. You sometimes hear philosophers saying, well, the speed of time makes no sense. It has to be 1 second per second. But that doesn't make sense, because when one talks about the species present, you're talking about your experience of the world. It's your mental time versus your physical time. And that's what changes. Sometimes time speeds up, sometimes it slows down. And somehow you've got to get that mental time into your picture of physics. But you won't get it through the normal four-dimensional description of special relativity, of general relativity, nor will you get it just through quantum mechanics. You have to go somewhat deeper. And so to me, that is the great challenge. How do you get your mental, your psychological aspect of the problem, how do you fuse that with the physical picture? And I think it can be done. My own particular approach may be crazy, but nevertheless, I do feel strongly you have to have some way of getting the species present into physics. And it sort of relates also to what Jayne was saying, because whenever you're talking about information rate is always relative to a species present. The smaller the species present, the bigger the information rate. And I think they're sort of like a hierarchy of species presence going, the Planck time itself is obviously one example of a species present, but I think there are others.
I think I'm having a meta reaction to people's comments instead of their original positions. But I'm a bit torn between, firstly, wanting to say that if we're ultimately going to put an observer into quantum mechanics, in some ways, then such an observer is going to have to integrate notions of what they perceive events to be, and then we'll end up with some kind of gradation of the type you're talking about. So ultimately, this effect will be incorporated. I don't however, believe that just because I can't experience events on a certain scale or a certain duration, that it doesn't mean to say that I can't actually witness effects which are consequences of something else going on which I can't actually directly experience. And therefore, I don't actually believe that doesn't mean to say that I can't make measurements or infer things about something else which is going on, irrespective of the duration or the gradation on which I actually interact with the environment. So firstly, I would think that physics could make a statement with or without a concept of species, for instance. But maybe to fully explain what we actually experience, maybe we need to incorporate other ideas. It's possible. I do believe that physics may not need these concepts. However, well, it's possible that physics actually doesn't need necessarily to incorporate a theory of cats. However, there would be a theory which is appropriate for discussing all these things, which is information theory. Information theory, everything ultimately is information. Everything in our universe, everything we experience, everything we describe is information flow. So ultimately, there is a theory, information theory, which should encompass and actually incorporate all these things, such as a theory of cats, which shouldn't need to be there specifically, but should be described by the overarching principles of information theory.
To answer Jim, I certainly don't want to give the impression that I think that there's no problem and there's no missing step in our understanding. There are plenty of missing steps in our understanding. There are many. But I think it's still a very good working hypothesis, and I don't see any evidence against it. To think that, it was in this way, thunderstorms, we don't understand them. If you talk to a person doing meteorology, thunderstorms are extremely complicated phenomena, electromagnetic, chemical, all sorts of things. We really don't have a good theory of thunderstorms yet. We all agree that. So there is work to be done on thunderstorm, and theoreticians, physicists, chemists are working on that. I don't think that there are many people who suggest that fundamental physics should be changed in order to make sense of thunderstorms.
Just Roger Penrose.
Thunderstorms?
No, I'm
I see the point. No, I see the point. It's a very good. It's a very good point. So I agree with Bernard completely when he says there's something missing here. Okay. We have some hints. Speech is present, 1/100th of a second, between 100 a little bit more. Has to do probably with the chemistry and the physics of neurons, which is at the same time scales, but we don't understand how it goes. So I fully am with you when you say there's something missing, there's work to be done here. There's work to be done in the measurement problem, there's work to be done in past entropy. Why early, it's completely mysterious. I mean, there are theories around, there's ideas, but there's work to be done on our brain, on consciousness. There's a lot of stuff. But I see no strong evidence from time or from else to push us to say that this is not necessarily like thunderstorms. It's just work to be done, not an indication that fundamental physics should be changed. When you and I work on primordial black holes, we tend to use fundamental physics so far. Then, let me address what you say, because I think this is a key point. You started by saying, then you came back, by saying, okay, unitary evolution, the world, it's time reversal symmetric, but the information I have is incomplete, and therefore, 100% with you, with a caveat. I believe that the I that has information, if I'm a naturalist, and I am a naturalist, it's a piece of the universe. So whatever theory of the universe in terms of information is information held by a subsystem of the universe that therefore should either be represented by the same laws of the rest of physics, or break my religion as a naturalist. Should I put it this way? So therefore, I don't think it's sufficient to say, oh, I trace out something, and of course entropy grows. Yes, clearly I trace out something, entropy grows. But you're assuming that the system you use, the agent that makes the measurement, that gather information, has already a time arrow. And if you check carefully, you're putting the time arrow from the system to the agent, and you haven't understood the time arrow, it seems to me.
So I think one way to pick up on this a little bit is that I think there's an agreement that something is missing, but is it emergent? Is the thing that will fill that spot emergent from the laws we have, and we know already, or is there some fundamental piece of physics that needs to be there that's missing to filter up? And for example, I happen to be of the camp that says, yeah, it's spectacular how much this community struggles with quantum physics, but I would say that's our problem rather than the problem of quantum physics, and I know that's not universally held, but that's sort of taking the emergent side on that. And so it's just kind of stirring things up a little bit. And I know Bernard wanted to tell us this crazy idea, so I'm going to hand over to him for just a couple minutes, because I think we all have crazy things we want to say. So.
Yeah, I sort of hesitate to tell you about my crazy idea because you just think I'm crazy, but I just want to give an example of how,
It's a badge of honor.
how in principle you could use physics to talk about, well, specious presence and all these other concepts. I'm very interested in string theory and M theory, and in M theory you have all these extra dimensions, and of course in the standard picture all the extra dimensions are compactified on the Planck scale, but we're also used to models where the dimensions can be extended, like in brain cosmology, one of them is extended. And I'm interested in models in which you have a compactification of, you have a hierarchy of compactification scales, and they go all the way from the Planck scale to much larger scales. And I'm interested in a model in which the specious presence, in some sense, is associated with the compactification scale. And so that you have a hierarchy of these specious presence associated with these compactification scales. Now, any string theorist here, I'm sure, will say that's completely crazy, because string theorists already face the problem that maybe their theories are regarded as mathematics rather than physics. And so if I say, well, those extra dimensions are something to do with consciousness, I'm sure most string theorists will not be comfortable with that. Nevertheless, I'm giving that as an example of how you can use standard physics, in the sense that this is what string theorists work on, to, not that everyone believes it, but at least...
So you're saying actually it is emergent. So when you say something's missing, you're actually using tools, sort of known tools, whether everyone believes them or not.
This is an example of a theory which is using standard physics, if you take M theory to be standard physics, and saying that itself may be adaptable to address the problem of a consciousness. And people may be uncomfortable doing that. It is uncomfortable to talk about consciousness because obviously it requires some paradigm shift, but the whole point is now that physicists do talk about consciousness. It used to be a taboo word 20 years ago, and now it's respectable, obviously, among neuroscientists, but even among physicists. And so maybe that's the way we have to go. But regardless of whether that theory is crazy, I still think the crucial point to study consciousness is the concept of the specious present. You've somehow got to get that into physics.
So any other comments from the panel? And then could the organizers maybe start, sort of queuing people up in the audience?
I just want to just sort of clarify that the sense in which I would think that something could be missing, and I'm not saying that I'm committed to the idea that something is missing, but that to pick up on the thunderstorm analogy, here's another kind of dynamical complex system, maybe not so complex, galactic dynamics, right? So galactic dynamics are something where I think we thought we ought to be able to understand this pretty well using just, ordinary Newtonian gravitation and visible matter, and we completely failed, and now we think there's dark matter. Dark matter is an example of new physics that we don't fully understand, something that isn't just going to emerge out of, squinting or coarse graining or something like that at the luminous matter in galaxies. It's actually something else that we have to put in to make sense of the dynamics of these systems. Now, there's another side to that, though, which is that there's this other community of people who have worked on modified Newtonian dynamics and who have argued that the kind of new physics we need to make sense of galactic dynamics involves changing the laws and not adding new matter. And the baryonic Tully-Fisher relation is the thing that they like to point to as the great prediction of Mond that cold dark matter couldn't do. But one thing that's happened, I think, over time is that as we've gotten more sophisticated in doing simulations of galaxies, we've come to understand that feedback processes, known physics that hadn't been fully taken into account in early work, can perhaps account for the baryonic Tully-Fisher relation, both its slope and the spread, much, much better than anyone ever imagined would have been possible. And so I think reflecting on that kind of example can show places where really there could be a missing piece. It doesn't mean that we're not naturalists. It doesn't mean that we aren't still doing physics. But nonetheless, that there's some part of physical reality that we don't understand. But it could also go the other way, that if we just take into account all of the details of these incredibly complicated systems, we're going to come to realize that we can provide the sorts of explanations that we're ultimately going to find satisfying without adding that extra piece.
So is there a pressing comment from the panel? And yeah, you look like you're ready. Good. And then I'm going to go to the audience as well.
So I actually wanted to respond to you. I was curious if what you meant was that since I say that the dynamics in the universe is unitary, that therefore I should also be able to say that, and therefore reversible, that I should also be able to reverse the experiences of the observer, the individual who's described by the same information theory and the same physical constructions as the rest of the universe, which I'm assuming has a reversible description. Is this?
Do you want me to answer?
Yeah, good. Yeah, so this is
No, the dynamical universe is unitary, but the state of the universe is low entropy with respect to the coarse graining that we use to describe it. That accounts for irreversibility. That's a fact, a well-known fact. Definitely, this uses the fact that we use a macroscopic description, namely we trace out of the... the question is what accounts for, why was the past... what I'm saying is that by itself, the fact of tracing out some variables doesn't give you a preferred time direction unless you add the past hypothesis. So either you add a past hypothesis or you make an agent time directed, but somewhere you're bringing time direction in, seems to me.
That's absolutely fine. To be honest, I would be working with the assumption that there's a past hypothesis instead of low entropy.
So Fred.
Okay, I'm Fred Adams. The question is this. I'd like you to explicitly bring into the conversation the concept of cosmological time. So as a cosmologist, you look at the scale factor as a function of time, and you think of that as describing at least the largest scale structure or the largest scale evolution of the time. In fact, you can measure time by how big the universe is, if you'd like. So the question explicitly is, if you measure cosmological time, does that arrow of time and that measure of time have anything to do with what you guys have been talking about for the last half hour? In other words, if you do an experiment in your laboratory, you stir coffee and milk together, does the arrow of time that shows up in those small scale experiments have anything to do with what's happening on the larger scale? Are they coupled, independent, or am I wasting your time?
They are strictly related because I think the large consensus is that the reversibility in the lab is related to the past low entropy. And because of that, if you're interested where past low entropy come from, you have to look past to cosmology. And it is a fact that I think is pretty consensus. There was an early phase in the universe in which the scale factor was small and matter by itself was pretty close to maximal entropy, to equilibrium. So then somewhere low entropy must be hidden somewhere. There are two ideas around. One is that it was hidden in the uniformity of the matter distribution, because once we fold in gravity, the high entropy configuration is crumpled. I believe this is not the right physical answer. The right physical answer is that the scale factor was small. So in a sense, the scale factor was small is one big variables strongly out of equilibrium. So the scale factor, the size of the universe, which is what you're referring to, the thing which has been growing for 14 billion years, it's a variable coupled to everything else, which has unsettled the equilibrium for very long. So yes, the two are related. There's a physical question. There are some papers describing that. There's some debate of which part weights more. I don't think there is a metaphysical thing, cosmological expansion versus thermodynamic expansion. There is a connection between the two. It's a technical thing.
Just to add to that, I think one point where cosmological time is very relevant is when you talk about the passage of time. You know, you've got this controversy over whether you have the block universe or whether you have the evolving block universe. And if you have an evolving block universe, there is always the question of how do you define the spatial hypersurface, because in special relativity, there's no preferred now. And as George Ellis has pointed out, if you have a cosmology, you have a preferred cosmological time, which defines the spatial hypersurface. So I would say, actually, when you're talking about the passage of time, you do actually need cosmological time. It does play a crucial role in singling out as a preferred spatial hypersurface.
So I've forgotten who it was that was saying that our awareness would be only in a sort of tiny region of Planck. Who was commenting that? Maybe one of the speakers this morning. Anyway, so I agree with these comments that we've heard, but I also want to say that there's this sort of collaboration. So the points, I agree with these points, and in addition, the way the universe is so incredibly simple is essential for tiny, tiny, tiny subsystems like us to deal with it. So there's this interesting sort of conspiracy among facts of the universe that allows tiny, tiny things to function as conscious, whatever, because if we really had to keep track of all the atoms in the universe to model it and keep out of trouble, we'd be screwed.
Okay, so the first one is the nature of time, emergent or fundamental. The second one is if time is emergent, and what does that say about the laws of nature? We can turn the question around rather than worry why the laws of nature are time symmetric. We can take a position on time and then figure out whether that implies that laws are emergent as well. And the final question is, talking of the problems of time in terms of information theory seems intriguing and promising, but I'm still not clear how that has helped us to advance our understanding of these deep problems about time, especially bearing in mind that whenever you talk of information and you try to address past, present, and future, that process, that kind of reverse engineering is very ill-defined. So I don't see how information theory can help us advance our understanding of time better than entropy and the previous concepts we have used.
So information theory ultimately gives us a way to actually describe any sequence of interactions. It's a lot more comprehensive a theory than, say, entropy, which is just one information theoretic measure of information propagation through time. So in particular, in relation to time, information theory ultimately, so time as a concept is currently, at least as I understand it, construed in the physical context as some kind of label given on a sequence of events. And then perhaps we actually also construe other constructs on top of that to actually interpret it as a conscious experience, maybe, or some sequence of, or reconstruction of the observer of their environment. So if I get to the point where I'm talking about time experienced by the observer as a reconstruction of their sequences of past events that they've flowed through, then ultimately I'm talking about as a simulation inside somebody's mind or a representation of the universe as they perceive it. So anything in this representation that I have, anything to describe this conscious experience must ultimately follow the laws of information theory, would be my statement. Because ultimately a simulation being acted by a physical system or a physical device, which is somebody's neural circuits, I assume. So you can tell I don't have anything to do with consciousness or neuroscience. So ultimately, any kind of construction we put on top of this will have to actually, should be able to be described by the laws of information theory and should obey any principles we can actually derive out of such a theory. So it should, well, whether it explicitly has a collection of tools which you will require to actually derive whatever question you wish to understand in somebody's conscious experience comes down to defining that question precisely. But ultimately, it should emit a complete description in the language of information theory, and therefore should be able to be studied and constructed in this way, in sort of a Turing machine sense.
Just to say that it isn't really just a matter of the problem of time, as both Jayne and Carlo have emphasized. It's really, you can only see the problem of time within the broader context of the relationship between your physical model and your mental experience, which may be some sort of informational space which relates to neuroscience and physics and psychology and everything.
To the thing you started with here in your title, is time real? Or so that, even more basic than the question of the direction of time, why does it even seem to flow, right? Which many of you on stage here have written beautiful papers on why is that such a hard question in quantum gravity and even in non-relativistic quantum mechanics, where, you know, if you think of it as just being unitary evolution, you have a vector in Hilbert space, it's just rotating and keeping its length, you know, why should some subsystem of this feel like time is flowing? And this, of course, as many of you have pointed out in your work before, crucially comes down to how do we factor the Hilbert space into subsystems? Why do we experience ourselves as living kind of in real space, not Fourier space, etc.? And you, Andy, for example, wrote this beautiful paper on the clock problem, pointing out that, yeah, things kind of work if you a priori say, this system we're going to call our clock, this we're going to call the rest, and then relative to the clock, things are changing. But if you monkey with if you give yourself the freedom to monkey with how you factorize the Hilbert space, you can make the seeming laws of physics change into weird things, or even make it seem like time isn't flowing at all. So my question to you guys is, do you feel that there's been major eureka moments, major progress in understanding this, like since you wrote the clock problem paper and so on? And if so, what are the main new insights we've had in recent years on this?
I'm going to start. Since you've sent that to me, I'm going to just make a brief comment. So my major eureka moment on that topic was to get myself into trouble, more trouble than I thought. So you might have thought that paper was all trouble enough, but I have this separate paper where I think all probabilities come from the Born rule, and we argue that. And so in the clock ambiguity, I was looking at ensembles of choices of clock and trying to derive some statistical statement about the laws of physics. And I've since had to back off because my generation of those ensembles was not legitimate according to my other views from this other line of work. And so I have, if you look on my website where I discuss that topic, I say now it's divided into two projects. One is the clock statement of the clock ambiguity, and one is, if you did have an ensemble, what would that look like? But I no longer think I know where that ensemble comes from, because it's actually, I was using the principle of indifference to generate it, and I no longer believe the principle. I think the principle of indifference is a bunch of hogwash now. So that was my eureka moment. Let's hear from some others.
I got to write a book on time and worry about time for long because of quantum gravity. And the super short story being the Wheeler-DeWitt equation doesn't have a time variable. What does it mean? And I am convinced that quantum gravity, in any way you formulate it, which seems reasonable to me, there is some analogous disappearance of time, which to a large extent it's what happening already in classical general relativity, which also can be formulated without any reference to the time variable if you use a Hamilton-Jacobi formalism. And the reason I insist on the layered structure of our common thinking about time is because once you realize that various aspects of temporality belong to different approximation or to different kind of systems you describe, then you're free in the fundamental theory, which is supposed to be the description of the largest phenomena, to forget about the sort of higher level aspect of temporality with a hypothesis to be confirmed, to be implemented, but seems to me completely reasonable, that they come from complexity, from entropy, from the approximation in which you forget Lorentz invariance because we're all moving at the same velocity and so on and so forth. So as you go down to more fundamental physics, you don't have a unique time because there are many Lorentz time, you don't have a preferred time lapse between two events because in general relativity clocks can measure different times and so on and so forth. And you go down to what?
So really wrap it up.
Yeah, you go down to what? To your definition of time, which seems the right one. Time is just a label of sequence event, which as a label, it's pretty, you can choose it as you want. And what dynamics describe the fundamental level is relation between variables without needing to specifying one as a time variable. The specification of the time variable comes from the approximation, the complexity, the thermodynamics, and so on. And the sense of passage, it's in our psychology. I'm not saying that I believe in a static universe, the other way around. The universe is a set of events, of things that happen, but they don't happen ordered in time. They happened, and we can label them with arbitrary time variables.
I want to thank the panel and the audience, and I think we've provoked a lot of discussion that we're going to have over lunch. So thanks, everyone.